guys. So this is chapter number 5. It's about parallel circuits. Okay. So resistance in parallel, first of all, when multiple resistance are connected in parallel, you can see here how we are going to deal with them and how will you identify whether they are connected in parallel or they are connected in series. Okay, so this is important to identify first. So you can look here the rule: resistors that are connected to the same 2 points are said to be in parallel. So here is a point. This is point number A, which you can see. This is just a line, and by the way, it is a point A. Similarly, this is another line. This is point B. We can see that between these 2 points A and B, R1, R2, R3, and R4 are connected. Same circuit can also be drawn like that, making this one dot point A, making this point as a B. Okay, so I can just show this way. I can connect these resistance this way also. So I can say now R1, R2, R3, R4. So both are same, but the difference is the shape. It looks more rectangular and more easier to look. Okay, they are in parallel, but the concept is the points are common, this point and this point. And this is what here, this is a just wire. So don't confuse with that one. It's just a wire. It means is that everyone is connected between A and B here. Is this clear idea?
Yeah.
Yes. Yeah.
Okay, so this is what we call parallel circuit. No. So a parallel circuit is defined by the fact that it has more than one current path. More than one current path. Okay, so now guys, if we connect a battery to this same common node, it is again a common node which we just discussed. It's again a same common node A. This is again another common node. Node is a point where 2 and more branches are connected. Current path or branches, yani the elements are called the branches. Like this is an element, it is a one branch. This is another, this is one branch, this is another branch, 3, 4th branch, 5th branch. So elements could be resistance, elements could be what you call yani voltage source, it could be current source, and so on, like that. Okay guys, this is like that. So now when we connect this battery here, so because of it a current will flow. Okay, let's suppose this is a total current, and now this total current will split here. And when it reaches to here, it will divide different currents. It will be like I1, it will divide into I2, it will divide into I3 and I4. It means is that can I say now IT is equal to I1 plus I2 plus I3, I4? Can I say this?
No, because the current is not the same in the parallel.
So who am I saying all currents are same? What I am saying?
They are added.
I am adding. I am not saying they are equal.
Oh, okay.
So okay, so this is the total current, which is now dividing into going into R1, R2, R3, and R4. So the total current is equal to the sum of branch currents is same. This is called KCL, Kirchhoff's current law. Do you know this one or not? KCL in physics.
Yeah.
Yani incoming currents is equal to outgoing currents. Sum of all incoming currents is equal to sum of all outgoing. So this is called KCL. We have KVL, Kirchhoff voltage law, for the series circuit. We have KCL for the parallel circuit. Okay guys, so this is IT, I1, I2, I3, like that. Now, so we can also calculate I1, I2, I3, I4 separately, but because of, as I said, this is a common node and this is a common node, right? And we are connecting here supply voltage Vs. So same voltage will appear to this branch, same appear to this branch, same appear to this branch, same appear to this branch. So what I can say, V1 is equal to V2 is equal to V3 is equal to V4 is equal to Vs, source voltage, because everything is in parallel. So all branch will be having same voltage. Is it clear?
Yes.
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 So it is different than the series. In series, what we have same current, but what we have here, voltage same. In
Which is the
series,
opposite.
yeah, in series we have different voltages, but here we have different currents. So this is the concept. This is the difference between series and parallel circuits. Now, so parallel circuit rule for voltage, because all components are connected across the same voltage source, all voltage across is the same. So if you have this circuit and if I gave you a multimeter or voltmeter to check the voltage across each branch, so you can connect here and you will see it's a 5 volt. If I connect to R1, it's a 5 volt. Connect to R2, 5 volt. Connect to R3, it's a 5 volt. So the thing is that in parallel, voltage is same. If I apply here 5 volt, everywhere it will be 5 volts. This is the property of a parallel circuit. Now, second thing, the resistance, parallel, a parallel circuit rule for resistance. So now, if you have multiple resistances connected here, how you will be calculating that the total resistance? Series is so simple. In series, what do we do? RT is equal to R1 plus R2 plus R3 and so on. But here, the formula is total resistance of the resistance in parallel is the reciprocal of the sum of the reciprocals of the individual resistance. So you can write this formula this way. You can also write this formula this way. Yani you need to get the reciprocal of all. Then you can also write this formula saying inverse. Is it clear?
Clear.
Yes.
Okay. So this is the formula to calculate the total resistance in parallel. So if I give you this example and ask you guys calculate the total resistance here. So you can see that this is in kilo ohm, this is in kilo ohm, this is in ohm. So we can convert it into kilo by dividing 1000. So we will be getting in kilo. Now we can put in the formula and we can get the answer. Can you get it answer easily now with using formula? By using this formula, you can get it, right? So what value will come? The value is 386. I know that you can solve it. That's why I'm skipping this point. You can calculate 386 ohm. Here is one point which I should bring your attention. Here is a rule, guys. When resistances are connected in parallel, so the total resistance, please focus, the total resistance will always be less than the least resistance present in the circuit. Total will always be less than the least resistance present in the parallel combination. If you check R1, R2 and R3, which one is the least resistance here?
R1.
R1.
R1. So you look here, R1, 680, right? Can you check
Right.
it? The total is less than this one or not?
Yes.
Less than.
Less than. So this is the rule. It can help you, this rule, while you are solving quickly. Is there any mistake or not? So whenever you are getting the parallel calculation, it should always be less than what you are having now. Okay, this is the rule. So this is the parallel. Now the special case when The resistances which are connected in parallel are of same value. So that formula which you know already, if you put there all resistance are of same value. So like if you say in that formula, if R1 is equal to R2 is equal to R3 is equal to R, when you put it, you will be getting this simplified version. RT is equal to R over Rn. Is it clear?
Yes.
What we are saying, all resistance are of same value. Let's suppose it is R. So when we put R in this formula, which we discuss, this one, everywhere, if you put R plus 1 over R plus 1 over R, you know, and for example, we have 5 here. So for example, let's see, this is one more inverse. So when you add it, you will be getting this one inverse. And when you finish this inverse, it will be like that. So now what is N here? The number of resistances. How many resistance we have? 1, 2, 3, 4, 5. So formula will be 100 over 5. How much you will be getting? 20 ohm. Clear now?
Clear.
Yes.
Okay.
Clear.
So it will help you, you know, during the examination, these special cases, because question may come. So you don't need to put the, you know, use this R1, R2, R3, R4 cases to solve that one, though you know special cases. So just quickly check the value divided by the number of resistance and you can get the answers without wasting much time. Okay. So this is the way, right? Now, this is the second special case. Is a second special case what we have. Here we have two resistances, and this special case is only for, you can just focus here, two resistance in parallel. So if you have only two, R1 and R2, you can, you know, apply that formula. So this is the same formula. Do you remember that with this formula we discussed already? Huh? So if we just simplify this one by taking you know, LCM and all, so we can have this version of this formula. And this is called product over sum rule. So it's so simple, just multiply R1, R2, divide with the sum, you will be getting the total resistance. Are you getting?
Yes.
Yes.
Okay, this is again in a special case. So these two special cases going to help you a lot. But by the way, this is not applicable for the third one. If for example, if I say one more resistance is there, and let's suppose this is R3. So this is, you cannot write the same way, okay? Because it's coming from that concept. Here you will be getting R1 and R2 LCM, then you will be getting R1 plus R1, then at the top one. So when you flip it, you will be getting something like that, okay? But it is not applicable for the third. Third, though you can just consider one more here like that, and that will come like that. So maybe if you want to remember, you can remember it. What it will be, RT is equal to R1, R2, R3 over R1, R2 plus R2, R3 plus R1, R3. Okay, so this is again a special or simplified version when three resistances are in parallel. Is it clear, guys?
That's clear.
Yes.
Okay, so this is any very important, necessary, you should memorize it, remember this one. This is any optional, if you can, that maybe is going to help you a lot also, because that version or this version, maybe it is more complicated for you. So the simplified, this version is more easy, whatever. But this is, and this is important, which is going to help you a lot. This one you can remember or you can ignore, it's your choice. Okay, guys. So this is a special case. Now, if the question come, for example, guys, calculate the total resistance. If R1 is this, R2 is this. Okay, you can just put the value in this formula and you can easily calculate. So the answer is, for example, 18.2 kilo ohm. Now let's consider this example to clear the concept. So we have given the value 5 volts here. For example, it is missing. I am writing here. Now they are asking calculate the current voltage par across each resistor. So guys, Please now tell me what should you do and how we are going to approach. What is the first step in order to solve that one?
Doctor, define the current.
Again, you are finding the current without finding the total resistance.
Yeah, but in parallel, calculate.
Okay. So what you said, you can say we can find the current in the branch. You
Yes.
are okay. Yes, we can do it. Yani I1, you are saying
I1 equals to Vs over R1.
V1 over R1, and at the top we can write I1 is equal V1 is equal to V2 is equal to V3 is equal to Vs is equal to 5. Is it clear?
Clear.
Okay, so 5 over
6,
680. Okay, I2 is equal to V2 over R2, 5 over 1.5. Please calculate quickly, guys, all these values. V3 is equal to R3. One can calculate another, one calculate another thing. Okay, so now we calculated all the currents, I1, I2, I3. Now what next? Tell me the values.
Doctor,
7.3 milliampere or
7,
7.35 milliampere.
7.35 milliampere. Very good. I2,
I2 3.3 million.
3.33. Always write 2 digits after decimal, guys. Okay. Next,
2.27
2.27 milliampere. Okay. Now, what next we can do? Is this all current or is there any current missing now? R total, Mohammed. Yes, exactly. I total, can we calculate the I total? It's not R total.
Yes, it is 12.95.
Okay, so there are two ways, right? Either we can just add them,
Yes.
or we can apply the formula. Which formula we can use it? Vs over RT. Remember, guys?
Yes.
So Vs is 5 and RT we calculated in the previous example, that was 386 ohm. Getting? That will come 12.95 milliampere. Clear? Are you getting? If you add them, if you add all these currents, check it. Are you getting the same or not?
Yes, the same.
Same. That's why I said KCL, Kirchhoff current law. Total current will always equal to the sum of branch currents. Clear? Okay.
Yes.
What next we can do? Voltages. Voltages we already calculated. This is clear.
Clear.
Yes.
All voltage are same, so no need to worry here. Next, power. How can we calculate the power now? Easy. Again, P1.
P so
There's
I
multiple ways.
IV.
Again, you are saying IV. You are not telling me specific formula.
I1, I1.
V1.
Yes.
Okay. Okay. Calculate that one. I1, I you already know. 7.35 milliamps multiplied by V5. Calculate this. Always see, I am writing formula for you people. Always write the specific. Don't write general formula. P is equal to V into I, because we are writing P2. So what value you will be using? Write that one. 3.33 milliamps multiplied by 5. And P3, I3 into V3. Then I3 is how much? 2.27 milliamps multiplied by. Okay, what values you are getting? Tell me quickly.
36.75.
36.75.
What?
16.65.
16.65. What is the unit?
Yes.
Unit.
What?
Really?
Oh,
What?
Milliwatt. Milliwatt.
Milliwatt. Yeah, be careful. I told you. This is important. You will lose your marks, quarter marks. If this question come 1 mark, you will lose 0.25 marks because of the unit. Next,
11.35.
finally, P3,
11.35 milliwatt.
11.35 milliwatt. Okay, add them all.
$64.75.
Milliwatt. Okay. Is there any other way to calculate the total power? Formula P total is equal to I total
I total, yeah.
into total voltage. Clear?
Clear.
Check this one. Are you getting the same when we are using this formula? 12.95 milliampere into 5. Check.
Yes.
Exactly, you will be getting same. Okay. So for the power, it is same formula, whether you have series circuit or you have a parallel circuit. There is no problem. Is it clear now?
Yes.
Okay, so this is the way to solve a parallel circuit, and this is the example, and we have given this one. Okay, so you can take a screenshot if you want. I am moving next now. Okay, maybe the tabulation is, oh, just a minute. Okay, yes. Okay, so now this is that they are having table here. So you can see V1 is same, I1 is, see they are writing their values 1 digit after decimal, but I advise you to write 2 digit after decimal always. So it is, that's why same. PT you calculated 64.75, but when they write only 1 digit, so this 0.75 will become 0.8, okay? Because of the rounding rule. We know we need to apply that one. So this is a parallel circuit. So guys, I just tell you one thing about the node and branches also. What is a node? Node is any point where 2 or more circuit elements are connected. And I told you what are the circuit elements: resistance, voltage source, current source, all are circuit elements. So if I ask you how many nodes are there, what is your answer about it? Nodes, yani where 2 and more circuit elements are meeting. So how many nodes are there? 2. Okay, first, is this the node?
No.
Yeah, is this the node? So we can say this is node number 1, right? Because any point where 2 and more, so here we are 2 elements are meeting, this one and this one. Okay, what about next?
Between R1 and R2.
So and you will say this one is a node, this one is node, this one is node.
No,
No,
just
no.
the first one.
Just the first one, yani this is a complete node, yani from here to here. Getting? Because this is a just wire. I told you this concept. Yani it's just this point and not different. Okay. So this is something like that. So it is considered as a single node. Okay. This is a single node. This is a single node. So any node number 2. Then any other node? What about this one?
Doctor from bottom, yes.
Okay, this is the third node, as exactly Faisal. So we have this with 3 nodes. Okay, here. So these are the 3 nodes. So hope the concept is clear about the nodes. What are the nodes now? What next, guys? Next is, this is highlighted, see? So node number 1, node number 2, node number 3. Next is branches. And I told you about the branches. Is so simple. Branches yani elements. So 1 branch, 2 branch, 3 branch, 4 branch, 5 branch. This is like that. So nodes and branches. This is the concept of nodes and branches. Okay. Yeah, it's a circuit element, Mohammed. So circuit element could be resistance, capacitance, inductance, current source, voltage source, whatever. So it is basically connected. It's called the branch. So this is one branch, 1, 2, 3, like that. These are the branches. So hope nodes and branches are clear to you. Okay. This is the KCL. By the way, I already explained to you KCL, Kirchhoff currents law. What it says that, what is the statement of the Kirchhoff current law? The sum of the currents entering to a node is equal to the sum of the currents leaving the nodes. Okay. Or another word, we can say algebraic sum of all the currents meeting to a node is equal to 0. So, for example, if I ask you in this question, calculate I. Can you calculate? Sum of the currents entering to a node is equal to the sum of current leaving the node. So first write and the current entering the node. So which are the current which is entering towards the node? Can you focus this? Entering. This is also entering. This is also entering. Yani. So 3 are entering. Okay, so we can just write. We can just now write, guys, entering nodes, yani 1.9 milliampere is entering, plus 0.5 is entering, and plus I is entering, equal to leaving. What are the currents leaving, guys? The node, yani going away.
R2.
Only this current, right? R2 current, which is 3. So now you can simplify. I will be 3 minus 2.4, which is 0.6 milliampere. This is the answer of this question. Okay, this way you can solve this one. And also we can say in a different way, like they are saying here, algebraic sum of all the currents is equal to 0. Yani we can say those are entering, we can consider them as a positive. Okay, those are leaving, we can consider that one as a negative. Look here, this is also leaving I3. Those are coming, I2 is coming, I4 is coming, so they are considered as a positive. So we can also say in other word that algebraic sum of all the currents, meeting at a node is equal to 0. This is KCL. Okay, guys. So Kirchhoff current law we can apply to this circuit. You can see this one. When you add these currents, you are getting basically this one total. This is here. So this is we have done here. Is it clear now up to now?